Welcome to my open learning session where I'm going to catch up with deep learning. We have reached chapter 2.1, Systems of Linear Equations. Systems of linear equations play a central part of linear algebra. Many problems can be formulated as systems of linear equations, and linear algebra gives us the tool for solving them. Okay, so the important part here is many problems can be formulated as systems of linear equations. So you have a problem and you can basically rewrite that problem as a system of linear equations. And then you just use the tools of math to solve it. It's super convenient. You have a problem in life and you can just use systems of linear equations to solve it. A company produces products N1 to Nn for which resources R1 to Rm are required. To produce a unit of product Nj, what? Aij units of resource Ri are needed. Okay, I goes from 1 to n and j goes to 1 to n. The objective is to find an optimal production plan, a plan of how many units X of product N, J should be produced if the total of B, I units of resource Ri are available and ideally no resources are left over. If we produce x1 to xn units of the corresponding products, we need a total of ix plus rn xn. Okay, I think before looking more, I would like to try to understand what they actually want. There are too many too many variables. I can't like I'm too slow in doing these things. Okay, so we have a company. Okay, I don't know. Let's say our company is called Food, and the company produces products N1 to Nm. Okay, so we have product N1 is, for example, an apple, N2 is a banana, and N is a coconut. Okay, wait, it's hard to draw. A pear. That's our pear. Okay, I can understand this. All right, so let's go and say we understood till here. So for which resources R1 to Rm are required? Okay, so we have resources. I don't know, let's just draw the resources here down. Okay, we have resources. Right now it's not clear, do I need all the resources for each product or do I just need one resource each? Like, do they share resources? I don't know. So I would not say that I have understood this part really. To produce a unit of product N, Nj, in this case, any of those N's, A, I, J units of resources Rm are needed. So we know that we have 1 to m for R and 1 to n for n. And this is basically the hint to like understand the relationship. Okay, so the i's belong to the resources and the j's belong to the products. So again, to produce a unit of product n, j, ij units of resources Ri are needed. So for in the n1 case, we need R. And how many of the R's do we need? Okay, I think I understand. We don't care which R is for which N. What we actually care, can I separate those? Yes. Would be nice if I had more space here somewhere. What what we actually care is the whole thing for each n. So here we have one n, and then we just assume that any r can go into this n. We can duplicate that for the next one, and we can duplicate that for the next one, and so on. This is what they mean. So we have R1 and R2 until Rm. And then we say that each of those products n, they just have a different ratio. So, and the ratio is the A. And keep in mind that A can be 0. So in case A is 0, it says that we do not need that resource. So what they are doing is they say R1, 1 is needed for RA. Sorry, R1. I think I just said something wrong. Again, A11 is needed for R1. And it's not enough space. I will just skip the RM part to make more space. Again, so A11 is needed for R1. And then A, and now we have to know that the first one is the I, and I belongs to R. So if we know that this is R2, this has to be 2, and the other one belongs to the product N. So it's 2, 1, and so on, until I will just use 2 lines for this. So for example, Rm, we need Am1. And this is times. So we need that many R1s plus we need that many R2s plus ... plus that one. So this is the what they call linear system, or it's actually a linear equation, and if you take all of those together, then you have a linear system. So the objective is to find an optimal production plan, a plan of how many units X, okay, where's X coming from? How many units X of product N should be produced if a total of B units of resource B are available and no resources are left over. If we produce X units, I'm here, of the corresponding products, we need a total of Ix plus of resource Ri. An optimal production plan where the X's are basically a tuple of Rn, therefore has to satisfy the following systems of equation. I'm not really sure what R is now, and I don't really understand what X is. But I think this is the general right direction. And okay, so usually you would know how many resources you have. So just thinking from the math standpoint, you don't know what n is because you don't know how many things you can produce. Well, actually, you know. If you know the resources, like you know how many resources you have, and you know how many units of each resource has to go into each product, you can actually calculate how many products you can make. Okay, let's say resource 1, we have 10 units of resource 1, and we have 20 units of resource 2, and so on, and maybe like 100 resources of resource M. A is not unknown, it is known, because you are making the product and then you actually know, okay, I need such, like so much of that resource to produce. Maybe Food Corp is not the best example. Maybe more something like, I don't know, Metal Corp, industrial something, making machines or something like that, where you have many different parts, which you can consider as resource, would make more sense. Yeah, so as you can see, this is what I call slow learning, step by step. I think it's like a mixture of understanding and remembering in my case. Okay, just because we know that A is known and R is known, this cannot be an equation. Like usually you would assume like an X or something like that. And this is where they come here with if we produce x1 to xn units of the corresponding products, we need a total of a total of equation many units of resource Ri. Okay, so I guess I figured something else out. This B is actually this one here. This is our B. We know that we have, in this case, 10 R1s and 20 R2s. And the question we really have is, what should we produce to have no leftovers? Okay, and what is X? Okay, this is the question we actually want to solve. The objective is to find an optimal production plan. Example, a plan of how many units xj of the product nj should be produced. Yes. And here I think there's also a problem from the beginning. The equation does not make really sense, right? Because like A has to be a number because it's like how many units. It's a quantity. R is a resource. It could be something like water or electricity or I don't know, like a resource, like a thing. And you cannot say that 2 times water plus 5 times electricity equals to 1 apple. Like the units would not match. The units, if the units they have to match, then the right side of the equation cannot be an n. The right side of the equation needs to have the same thing, the same unit. And this is a thing what they give us here as a hint, basically first. Not a hint, but they say, okay, let's just think. A is basically the weights, the balance, what is it? How many of that do you need for that thing? And X is the resource, I think. But the quantity of the resource. I feel stuck. Maybe it makes sense now to go and read the next part. Aha. An optimal production plan therefore has to satisfy the following system of equations. They say A1, I'm here at the bottom, A11 x1 plus A12 x2 plus A1n xn equals B1. And B1 was the quantity of the resource 1. So the right side is not this one here, like it's not n. The right side is the resource. And not just the resource, but the quantity of the resource. So you would have something like 10 equals A plus x1 plus A something else plus x2. And in this case, they are not the same A, but the A belonging to the resource plus the A which belongs to the resource and the A which belongs to the X. So 1, 1 and 1, 2. And then you will have the next equation, which is 20. Then you have 2, 1 plus x1 plus 2, 2 plus x2. And this goes on. Yeah, so I'm not really sure how the relation is from the x and the r. Maybe I'm reading it wrong. Let's read it again. The objective is to find an optimal optimization plan of how many units xj of product nj should be produced. What? A plan of how many units xj of product nj should be produced. How many units x should be produced if a total of b units of resource are available. So we know that j is part of, like, has a maximum of n. So like if we just put this in a matrix, we know that we have two dimensions. We have here one dimension and we have another dimension here. And they usually go with the letters m and n. So here we say m and here we say n. We know that if I'm trying to just find like a different reasoning, if x is j, like we have j-axis, which is from 1 to n. This gives us the hint that the x's are here. And each row of those x's, they have to be n rows. The length of the row, which means the number of columns actually. Oh man. So how many columns do we have? N. So how many x's do we have in one row? We have n many x's in one row. That makes sense because we have here x is xj and j goes from 1 to n. We know that b is an I. So how many b's do we have? We have m b's. Okay, just knowing those two have different dimensions, we can already put them in different categories or sort them already a little bit. Okay, so the link here is it says that xi1 x1 plus and so on many units of ri, and we know that ri, like the link is here, they say units of resource r, and the actually amount, or like the quantity of exactly that unit of resource r is b. So this is so confusing. Like step by step, I'm going to deconstruct that in my head. Okay, so this makes sense so far, I think. Okay, I think another sentence which I misread is this one. If we produce x1 to xn units of the corresponding products. So we have here our products n with the index j. Then what they're saying is each x is the unit of how many of those products you produce. So for example, if x1, like x1 corresponds to n1, that means these are apples. And in the next equation, we have here apples as well, but the amount of apples. So we want to produce, we don't know how many apples we want to produce. We just know that apples it takes this resource R1, 10 amount of that resources to produce like an apple. How many of that resources we need? That's basically this A. In the case of, let's say let's say R1 is not water, but R1 is glue, and we do not need glue for producing apples. That means that this one would be 0. So no matter how many units of glue we have, this would not affect making apples. So the initial confusion here was that I assume the right side is are the products, but they are not the products. The right side are the units of resources. And the products actually are here. How many of those products we have. And the coefficient, in this case, A, is the relationship of how many of those products relate to the resources we have. Let's read it again. Let's read the whole thing again. I'm going to delete it all. I do not think that there's much value keeping those writings. Okay, so let's read it again. The company produces products N1 to Nm, for which resources R1 to Rm are required. To produce a unit of product N, J, so one of those products, Aij units of resource R are needed. The objective is to find an optimal production plan, a plan of how many units X, J of product Nj should be produced if a total of Bi units of resource I are available. No resources are left over. If we produce x1 to xn units of the corresponding products, we need a total of A I1x1 plus A I n xn. Many units of resources Ri. Okay. So they are saying that, yes, it makes much more sense now. We know that we have that many resources of each R. In this case, we have B1 resources of R1. And we know that the product N1 needs that many of B1, basically. They're basically drawing from the same pool of resources. So the apple is drawing from the resource, in this case, like the first product is drawing from the same pool of resources, and the second product is drawing from the same pool of resources, and so on until the last one. And then we have the same thing for the second or the last resource. There's a pool of resource for the last one, like, I don't know, like glue, or let's say glue. And then you have the same product, and now we just want to know how many resources they need and how much they are drawing from the pool. And this is the second pool, or in this case the last pool. So you have different pools of resources, and you just state how many resources you need for each product. So in this case, B is known, A is known, and just X is not known. Yes, and the tricky part is to get not confused here. I hope this makes sense for you. Okay, let's go on. Equation 2.3 is the general form here. Is the general form of system of linear equations, and x1 to xn are the unknowns of the system. Yeah. Every n tuple that satisfies 2.3 is a solution of the linear equation. Okay, so the solution is a tuple, like a list of x1 to xn. So let's say n is 10, then the tuple would be, or the array would be 10 entries. And there's not one combination, but it could be many different combinations which lead to a solution. Maybe there's 0 solutions. Okay, so here they have an example 2.2. Okay, example 2.1 was quite heavy, to be honest. Now I hope example 2.2 2.2 is easier. And then we are almost finished with this chapter. Okay, so example 2.2, the system of linear equation. So in this case, the system is already given. So we have three equations, and we have three x variables, x1 to x3 here, and we have a scalar. This one is a, basically. This one is an a, this one is an a. There are different a's, and the one which is left out is 0. So what they can do is, if we remember, a vector is something you can add together and get a new one of the same thing, or you can multiply it, and that's actually true here as well for the equations. So you can add, what they're doing here is adding the first two equations, so this one and this one. So 1, 1 is 2, this one that one cancels each other out, and this one is 5. So we have this equation, which contradicts the third equation. Yes. So it says 2x plus 3x, which is exactly this one. And now this equation says 2x plus 3x is 1. And this equation here says no, it's 5. And this is what they mean with contradiction. Okay, now they go just to a different example. Let us have a look at a system of linear equation. Again, some equation. From the first and third equation, it follows that x is 1. So how do they know that? They subtract. So adding and subtracting is the same thing. So they do 1 minus 3 equations, right? So the first one still remains x1. This one cancels each other out. That one cancels each another out. And here we have minus 2, I guess. What do they say? Oh, sorry, it's not minus 2. This one is 1, because we have 3 minus 2, and that is 1. All right, just cleaned it up. So yeah, x is 1, and what they are doing now is they adding the first and the second equation, and then you will get something like that. That makes sense, because this one is 2, that one cancels each other out, this one is 3, this is 5. So we have x1, which is 1, and then we have x3, which is 1. And then if we just plug x3 here, then we're getting x2 is 1. Therefore, 1, 1, 1 is the only possible and unique solution. Okay, and we can plug that in, and then we will see that it will work. Okay, next example. Again, equations. What they are saying is if we add the first and the second, we will get the third, which means that you can think of that this is the third one does not give us any new information. So that's why they are omitting it. So the third one is omitted. And now we have a problem. We have two equations and we have three variables. Okay, so I'm not sure how they are getting this one here. I guess, well, let's try just to add those two equations. So what we are doing is 1 plus 2, the equations. Then we have 2x1. That one cancels each other out. x2 plus 3x3 equals 5. Then that one can go over here. Yes, then we have something like that. So this thing is now that thing. 2x equals 5 minus 3 x3. Okay, so the first equation I understand how they're getting it. Now the question is, how are they getting the second equation? So here we have the x2. The x2 is still alive. So I think I can do that by doing equation 1 minus equation 2, which means that x1 cancels out. We will have minus x2 minus x3 equals, now what they're doing is they want that over there. Oh no, I made a mistake. Here is a plus. Yes, now it makes sense. Now we can just move that one over there, and then we have 1 minus x. Okay, so what they have done is they just multiplied and then subtracted to get the first equation and to get the second equation. Now what they're doing is they define x3 as a free variable. x3 is going to be a. So why x3? I think because it is present in both of those equations. I think it's like a trick or so. Okay, and I think once they have just defined it as a free variable, they just do another set of equations. Here we would have 2x2, x1, I guess, equals 5 minus 3a. And the next one would be, no, you don't even need to do the equation. What you need to do is just to plug in the numbers, because the solution here is for x1 and the solution here is for x2. So what they are doing is they just solve that equation. So they solve that, and this is the first part, and then they solve the second part, and it goes here. And if you take it, okay, let's put some colors in. Okay, x1 is green. This is a solution for green. x2 is yellow. This is a solution for yellow. And x3 is blue. And we know that because we just define x3 as a, this one is a. So this is a solution. And as you can see that anything which satisfies this one is a solution. And a can be anything from the set of real numbers. So you have infinite solutions for this equation here, for this equation. So yeah, this is what you usually learn in high school, that the number of equations has to match the number of of the variables. Otherwise, you will not have one unique solution. What is the next one? Yeah, it's basically what we said. It has infinite many solutions. In general, for a real valued system of linear equations, we obtain either no, exactly one, or infinite many solutions. Linear regression solves a version of 2.1 when we cannot solve the system of linear equations. Okay, what was this 2.1? This one, the one we struggled with. Okay, so 2.1 was actually solvable because we had all the information. We had all the, yeah, as shown, it was solvable. But in case it's not solvable, like it's not solvable with a system of linear equation, then what we do is linear regression. So I think this one is important. Linear regression solves a version of linear equations which cannot be solved with system of linear equations. Okay, next one is remark, geometric interpretation of systems of linear equations. In a system of linear equations with two variables, each linear equation defines a line on the plane since a solution to such a system of linear equations must satisfy all equations simultaneously, the solution set is the intersection of these lines. This intersection can be a line if the linear equation describes the same line. A point or empty when the lines are parallel. The illustration is given 2.3 of the system. So we have here two equations, and because we have two variables, we can plot them as lines on a plane. And what they're saying is if there is an intersection, then that point of intersection is the solution. But it could also be that they are parallel. So let's say we just draw another blue line, and the equation for blue would be different. So if blue would go like this, then there would be no intersection, and like these lines are like infinitely long, and there would be no intersection, so it means no solution. In case of they are actually on the same thing, like just imagine they're on the same line, then you would have infinite many solutions, because the intersection would be infinitely dense. So similarly, for three variables, each linear equation determines a plane of three-dimensional space. When we intersect these planes, example, satisfy all linear equations at the same time, we can obtain a solution set that is the plane, a line, a plot, or empty. So it's basically the same thing, just one dimension higher. From the plane point of view, you can say, okay, like a line is what the best you can do. Then you have a point. Then you have 0 points. From a 3D space, then a plane is the best you can do. Then you have a line. Then you have a point, and then 0 points. Yeah, it makes sense. It's just one dimension higher. For a systematic approach to solving systems of linear equations, we will introduce a useful compact notation. We collect the coefficient, the a's, into vectors and collect the vectors into matrices. In other words, we write the system 2.3 in the following form. So we have our x, and then we just use a vector for each of those. Yeah, that makes sense. But this is the same thing, basically. It's just a different way to write it. So you can see that that thing is the same as this thing. And what they have done is they pulled all of those together. All of those coefficients, they pulled together to form a matrix. Then they took all of the a's of the x's, and they pulled those together here. Yeah, so the problem is if you see a compressed version and you have not worked out how this actually is being constructed, then it's too dense usually, at least for me. That's good. In the following, we will have a close look at these matrices and define computation rules. We will return to solving linear equations in section 2.3. All right, so I think the next chapter is about, it's matrices. And then we will move on. Yeah, okay, thank you.